Marjorie Chan. I'm Professor of Geology and Outreach. And we're really excited and very happy to have all of you here for one of our annual open houses. There's a lot of work to put these on, and so we have actually scaled back to just doing this once a year. But we also have a number of department lectures and campus lectures on sustainability. There's really a lot of exciting things going on on campus, and we hope that if you have the opportunity, you'll get involved in more of the different events that are being sponsored here. I have the pleasure of introducing Dr. Barb Nash, who will be giving our lecture this evening. She was just this last July appointed emeritus professor. Those of you that are over here, you can feel free to come over here and sit in the front. She has been here at the University of Utah for 50 years, and it's been an amazing career that she's had. She trained in geochemistry and petrology, where she received her PhD at the University of California in Berkeley. And upon her arrival here, she established the Electron Microprobe Laboratory, which has been in continuous operation since, and that's been an extremely important part of some of the research that goes on in the department. She's characterized many alkaline rocks to understand their formation, and she's explained and studied a lot of the explosive volcanism of the western U.S., and she's also been a key analyst in some of the work involving correlation of ashes, tephra, and obsidian in human evolution of East Africa. She's also been involved in characterizing minerals that are unique to the Anthropocene, which I think she'll talk a little bit about today. And a few years ago, she had a newly discovered mineral that was named after her. It's called Nashite. And Barb has actually been involved in the characterization of 77 newly recognized minerals on Earth. So really, she has been at the forefront of mineralogy for quite some time. She served as the department chair of the Geology and Geophysics, and I know that she was doing a great job because she hired me. And most recently, she has served as the Associate Dean for Research for the college. She's a fellow of the Geological Society of America, and in 2015, she received the Mineral of the Year Award from the International Mineralogical Association. So Barb has really just been a very vital part of this department, and she is well known as being an artist. She actually helps me and the committee in many of the designs of this building that we've enjoyed over the years. So I'm really happy tonight to be able to introduce Barb to share her story on minerals old and new.
Thank you for that generous introduction. Did she say 50 years? Maybe I should sit down. I was going to say when I first started here, I could say a half a century ago, but that sounds even worse, I think. I would say 5 decades ago when I arrived here, I taught mineralogy for about the first 10 years when I was here. We were on the quarter system then. We're on the semester system now. We were on the quarter system then, and mineralogy class took 2 quarters. It was 2/3 of a year. And so you can imagine that if I'm going to cover all that material, I have to get going here, you know. I can't possibly do that. So what I am going to do is first give you a list, which I know you'll be horrified, but this is an outline of what I'm not going to talk about today. Because there's so much. It's so important about mineralogy, but I'm not going to talk about strategic or dwindling natural resources, but that's something that we do worry about. I'll touch on it maybe towards the end. Key templates for engineering new materials, and we have a new merged department in our college now, material science and engineering, where they're engaged in engineering new minerals, and often minerals are great templates for this. They're important in waste disposal and remediation of pollution. Bill Johnson in our department works on this. As pollutants move through sandstones, how do they interact with the minerals that are there? Minerals interact with the atmosphere. That's related to climate and global change. Gabe Bowen works on those things. Chemistry, formation of the rocks. Rocks are just aggregates of minerals. That's really important in the Earth's internal dynamics. So we have people here that are reproducing the conditions deep within the Earth to understand how it circulates. Lowell Miyagi's doing that. Volcanoes, Sarah Lambar can tell you about that. I won't. Geothermal systems, John Bowman works on those. Shale gas, Lauren Bergenheimer. Human health, very important. All those PM10 and PM2.5 particles, lots of them are minerals. They're something we really need to understand. Diego Fernandez looks at those sorts of things. Okay, so that's what I'm not going to talk about. Let's first see if we can understand what a mineral is after we go through this process. It used to be, when you're asking about a substance, was it animal, vegetable, or mineral? And here's a beautiful mineral from southern Utah that was discovered about 3 years ago, not me. It's called red canyonite. You can guess where it's from. Red Canyon at the Blue Lizard Mine, discovered about 3 years ago. Just beautiful, beautiful mineral. And we got some minerals here in front. This is some quartz. I think you can kind of see these. We tried to get some that was a reasonable, as big as we could carry, large enough to get in here. And this is a barrel here. So oops, wrong button. So here, it's a pretty simple definition for what a mineral is. And so it's an element or chemical compound that's crystalline, and that means it has its atoms or molecules in some sort of regular array or order. And it's formed as a result of geological processes, so it's forming naturally. So if we synthesize something, we make it in the laboratory, that's not a mineral. So we can see this ordered structure, and I'll show you some in here. And this is a nice ordered structure here, but it's pivot irrigation in Saudi Arabia. Okay, so barrel. Here's the barrel here, and I'm just going to use it as an example. You can see where it gets its name. It gets its name from beryllium. It's a beryllium aluminum silicate. It's a pretty simple thing. Some of you have seen this beautiful red beryl that we have here in Utah. It's really precious mineral here. So beryl, and this is how crystallographers kind of represent these crystal structures. It's maybe not immediately obvious, but if you look at this beryl here, I think you can see it's kind of hexagonal in shape. I don't know if you can sort of see it. The quartz here is too, actually, is hexagonal. And that hexagonal shape comes from how the atoms are arranged in the interior. So that's the crystalline interior. And this is remarkable. This is a transmission electron microscope. It's looking down the barrel of the barrel, right? So like this way, down here. And you can see the individual atoms. So all of these little white dots are individual atoms. And they're color-coded here. I gave away I'm going the wrong way, but this is my new. So this is a mistake of using a new device, right? I'm going the wrong way with it. But you can see the aluminum atoms are green, the silicon are blue, the oxygens are red, and the barrels are too small. The beryllium's too small to really see. But you can see the order here, the hexagonal shape in the aluminums, and that's what you see here reflected on the external shape. So that's what we really mean by a mineral. It has kind of a reasonably well understood, fairly simple chemical composition, and it has this internal structure, and it forms naturally. Okay. So what I want to talk about first is an exciting new concept or way of looking at minerals. And this has emerged just in the last decade. So I think it's really important, and it's almost a revolutionary way of thinking about minerals. Rather than just classifying them by that chemical composition and their structure, we have another way we can look at it. And by mineral evolution, I mean that how the abundance, the number of minerals and their diversity has changed over Earth history. This is not the same thing as biological evolution. It's not the same sorts of mechanisms, but I think I hope to persuade you that actually biological evolution and mineral evolution are going hand in glove throughout Earth history. But we want to talk about its change over Earth history. So it's not Darwinian in that sense. Minerals don't change from one mineral into another readily or go extinct, but rather it's just this change with time. Like you would talk about the history of the automobile over the last 100 years or something. All right? So just to be clear, Darwin here he's secure, and we're not challenging the biological evolution. And this has emerged in the last 10 years, and I'll just be really quick on this, but there are 3 major publications here in the last 10 years, all led by Bob Hazen at the Carnegie Institute. The first one was in the American Mineralogist in 2008, Mineral Evolution, and then a whole journal devoted to it 2 years later, and also Scientific American in 2010, Evolution of Minerals by Bob Hazen. And if you find this interesting, after I've been through it, if I persuade you it's interesting and want to pursue it anymore, I would really recommend the Scientific American article. It's reasonably short and not too technical. Okay, so history, Earth history. So this is a diagram. It's drawn by an internationally famous artist, Andre Valley, whose husband happens to be a geologist. And so this diagram is sort of informed by this information, and it's a beautiful diagram, and it's useful. This is the timeline for Earth history then, starting over here at the beginning of the Earth, 4.56 billion years ago, and then running over here to the present day. So here we are. So that, and I'll come back to this with this diagram several times. So we're going to start, I'm going to start actually a little earlier than the Earth, but already I've given away one bottom line, that biological and mineralogical evolution are tied together. The other bottom line here is that mineral abundance or diversity has changed over Earth history, and at the beginning of Earth history there were about 250 minerals when the Earth first came to be, and today there are about 5,700 minerals on the planet. So this is a big change, and what we want to explore here is how do we get from this small number to this large number today, and where does this tell us about what the future might hold for minerals on Earth? All right, so I want to start a little earlier than the Earth and go back to the solar system just to start with. Here we have the solar nebula, the sun is there, there's dust accumulating, and condensing out of these hot gases, very high temperature, were a few minerals, but not very many, about probably 60. Diamond would be one of them. And we know these because there's a class of meteorites called chondritic meteorites that fall to Earth, and they're relatively undifferentiated from the earliest stages of the solar system, and they altogether contain about 60 minerals. So we know that's sort of the starting point when you are going to begin to make terrestrial planets. In that process, then you form these sort of larger bodies, planetesimals, and these are bodies then that are accumulating gravitationally, but they're also smashing into one another, and there's some melting going on. And so there is new mineral creation taking place in this process, building up to where you accumulate all of these into an Earth-sized body. And if we look at all the meteorites that we find, they have about 250 minerals. So that tells us that's the starting point for the Earth. We start with 250 minerals. Here is a meteorite on the surface of the ice in Antarctica. Jim Carner in our department has a table up on the third floor here at this end, which is, he calls it meteorite or meteorung. Can you identify them? Is it a meteorite or is it not? I recommend go take a look after the talk. And he runs this program that finds meteorites in Antarctica, and they've found thousands there. It's absolutely amazing. Here's a beautiful iron meteorite with olivine crystals in it. Some of them are striking. Okay, we're at 250. So here we are now in the early stages of the Earth, and this period of time is referred to as the Hadean. That's Hades, or hell, hellish sort of place that was always envisioned to sort of be like this, with molten material, steam, sulfur, and whatnot, due to the large amounts of melting. Early on in Earth history, we had a major impact. A huge impactor spun off part of the Earth, proto-Earth, to make the moon. And so we have the moon formation, a lot of melting, crustal melting around both bodies, the Earth and the moon. And then increased mineral diversity, as you can see up here in the third bullet, from continuous sort of volcanism and crystallization that's going on. So we develop a variety of rock types, of igneous rock types, basalts to granites early on. And then the Earth is outgassing, so it's forming its atmosphere. And the atmosphere is going to be anoxic, no free oxygen in it. So it has nitrogen, has carbon dioxide, has water in the atmosphere. And we also have a hydrosphere, so there's water on the surface, and this water can interact with the 250 minerals that are already there and create more minerals through that sort of process. So that would be going on. Okay, so that's very early on, and we're going to return to the Hadean because we've learned a lot more about it from analyzing zircons, and I'm going to talk about that later in the talk. Has that got everything there? I think so. So we can move up to the Archean. Oh, so backing up. So this process here, the water and all those, now we're up to about 1,000 minerals on the planet. Okay. We're trying to get to close to 6,000, but we're at about 1,000. So here we are now in the Archean, from almost 4 billion years ago to about 2.7 billion. And this is a time when the planet becomes more dynamic. Subduction is beginning in here somewhere. Continents are beginning to form. The atmosphere hasn't changed very much. No free oxygen. But there is some rise of microbial life. But it doesn't seem to have much effect on mineral density, diversity. But we do have sediments here in Greenland at about 3.8 billion that have some isotopic evidence of life, organic processes going on. Fossils in chert. Over here, these squiggly looking things, which I haven't bothered to show you in any detail. Most recent paper, it's just a year ago, shows that these are from their carbon isotopes, that these were organic processes that were going on, bioprocesses here. And then finally cells with nucleus here. So we get a little bit of diversity, and maybe we're up to 1,500 minerals on the planet. Anything else? Okay. Then, here, circled in red, big red letters here, this is the GOE, the Great Oxidation Event. And it occurs around 2.2 or so billion years ago. And this was profound. So here we had the rise of photosynthetic plants, cyanobacteria, and organisms that were producing now oxygen into the atmosphere, and the atmosphere now had a little bit of free oxygen in it. Only maybe 1 or 2% of what we have today, but it didn't take very much. And that was sufficient to change the planet from a reducing kind of environment to an oxidizing environment. And in a very simple sort of words, the planet rusted. The iron that we had would oxidize to ferric iron, and all of a sudden we had an abundance of all kinds of new minerals from all of these different elements that had all of these other various oxidation states. So we think about another 2,500 minerals emerged once we got this free oxygen into the atmosphere and onto the planet. So these huge number now of minerals, bringing us almost to 4,000, owe its existence primarily to this biological activity here that's producing all this wonderful oxygen that we so depend on today. Okay, then quickly, because I don't want to spend too much time on this, the next period of time between about 2 and 1 billion years ago, nothing much happened. A lot of people called this the boring billion. If you work in that period of time, you probably take offense at that. But anyway, this is not much happened, and it's pretty much nothing much happened new mineralogically. And then we entered into a period of time when the planet got a lot colder, snowball Earth. There were glacial periods and interglacials. Ice was a dominant mineral at that time, but the planet continued to be active. So we're still somewhere around 4,000 minerals now on the planet. And now I want to go and look at the last part here of Earth history, the Phanerozoic, the last about 500 million years, a little more than that, from the Cambrian on. This, of course, is the period that we know that has all of the abundant fossil evidence, because now we have animals with hard parts, trilobites, dinosaurs, us, these sorts of things. And we see, of course, the great effects of Darwinian evolution through this period of time. And that's what the fossil record has taught us. At the beginning here, we still, the parts of the planet that were above sea level were still pretty much bare rock. But by about 400 million years ago, plants began to occupy the land surface, and they produced lots of soils, and soils produced these biologically active clay production, and what some people call the clay mineral factory. And we produce lots more minerals through that process. So the life processes here are driving the mineral formation. So we're up to maybe 4,800, something like that. And in this period of time, then, there are all kinds of mechanisms for biomineral formation, from organic precipitation. You can see them here, oxalates, so it's carbon, oxygen compounds, carbonates, phosphates, oxides, hydroxides, sulfides, all kinds of things going on. These are some scanning electron microscope images, high magnification. This gooey, smooth stuff up in here is a biofilm, organic material, and growing on it in close continuity and contact with it are selenium and sulfur granules. These two sort of fibrous looking things down here are actually fungus, and here are uranium minerals growing on the fungus over here, and here are these calcium oxalate minerals, these squares and other cubes growing on the fungus over here. So they clearly have an intimate relationship, and I guess that's the takeaway that I want to leave you with you here in terms of mineral evolution. It'll have some implications. Let's see. So yeah, here's some of the thinking about what are the implications. And if we understand that the diversity of minerals that we see on the planet are related to evolution of life on the planet, then there are some consequences when we start looking for life outside of our planet or even outside the solar system. But you look at the moon, here's a nice, beautiful color image of the moon relating to its geological features. When you look at it, we see basically an arrested development here. The last lavas are probably maybe 1 billion years old, but most of it was even earlier than that. No oceans, no life, and as far as we can determine, the moon itself made only about 30 minerals itself, and so it really wasn't very productive. Mars, and this is what Margie has focused on a lot here in her research, and you can correct me if I say something really outrageous here. Certainly there's potential for life. We're very interested in that. And part of the reasons, of course, is the evidence for ancient oceans, clay minerals that have been worked on and discovered there. The oceans are no longer there. They've evaporated, and we have evaporites, which are on top of a lot of the clay systems. So we have the drying up of the oceans. There doesn't appear to have been any major oxidation event. Is that safe to say? I got a nod over there. Thank you. And there are some, but it's a red planet. So, but what's happening is that water vapor up higher in the stratosphere of Mars gets dissociated by solar radiation. The hydrogen goes away, a little bit of oxygen is around, and it's sufficient to sort of rust the planet, but there's no real free oxygen in the atmosphere. So must not have been a great oxidation event on Mars. And that, of course, drove so much of the mineral diversity on our planet. This is Mars. Isn't this incredible? I look at this and you can't you? I just think we're down. Why is Utah such a great analog for Mars? But here we are. This almost looks like the Chinle, and maybe this is the Cayena. And here's the Navajo sandstone on the horizon at Capitol Reef. It's extraordinary. I think quite amazing. But didn't get as far as Earth in that way. So the real question is, can we recognize biosignatures in other planets or even in exoplanets out in other star systems as we get more information about them? I just want to direct your attention to a really remarkable paper that just came out. Margie's the co-author with about 24 other authors looking very closely how can we recognize biosignatures in a planetary context, which I think is really important. All right, so that's what I want to say about mineral evolution. I want to just do a little aside, since I'm talking about planetary things, to talk about moon minerals. I had the opportunity early on when I was here, first came here, to work with the Apollo program. Actually worked on samples from Apollo missions 14, 15, and 17. And two minerals I wanted to show you that were found on the moon. One of them is armalcolite. It looks like this. It's an iron titanium oxide, so it's opaque. It's a lot like magnetite or hematite. This is looking down the microscope. You can see the reflectivity. This is from Apollo 7 mission. The reason armalcolite is worth remembering is who were the first 3 astronauts that went to the moon? Armstrong, Aldrin, Collins. Good. If you ever have a problem remembering, it's Armstrong, Aldrin, and Collins, and that's, of course, armalcolite. And it was discovered at Tranquility Base from where they landed a little over 50 years and 3 months ago. Is that right? We just celebrated the 50th anniversary of the first landing on the moon. This is a a lunar basalt. This is one that I've worked on from Apollo 17. Just a pretty picture, but a beautiful olivine crystal with some feldspar. Okay, and then the other mineral, maybe my favorite mineral name. I don't know. I have a few that I kind of like for different reasons, but you see what you think. How about tranquilityite? We could use a little tranquilityite, I think, in our lives. And this is a picture I took of one from, it's the Apollo 14 mission. They're very small. They're beautiful little warm foxy red crystals. They're an iron, titanium, zirconium. Oops, I'm having trouble with there's a little zirconium in it here too. So February 17th, and then here's another lunar basalt from Apollo 17, December 1972, and we haven't been back yet. Isn't that extraordinary that we went there, many number of missions, and then we just let it go? Well, we need to go back. Both these minerals have been found on Earth now, interestingly enough. The tranquilityite's been found in very, very, very old basalts. And of course, here it is on a very old basalt on the moon. So this was the sort of coevolution of the Earth and the moon. Okay, so that's my story about extraplanetary minerals. So now I want to turn to just an example of how minerals can be really useful to tell us some important things that we might want to know. And I'm going to take as an example zircon. But just going back to looking at, so when you see one of these things here and you say, well, first of all, if you're a geologist, my hand lens is in my bag over there, so I can't pull it out and look at it. I could shine a laser into it. It looks pretty cool. Can you see that? Anyway, so we're doing a little laser analysis of this mineral here. And so the first question sort of is, what is it? We'd like to know what it is. What do you think, as an earth scientist, you might want, what's the next question you might ask? Anything's okay. I have my own next question, but particularly if we're thinking about Earth history, how did it form? All right, that's one. Yeah? Where was it found? Good. Yes?
How old was it?
And how old? That's what I want to know. Yes, right. He said, say it out loud here.
How old is it?
How old is it? Yeah, we want to know that. You're right. Excellent. You're hired. Okay, so zircon. So zircon is really useful, and it's a fairly. Let me go back. Has a really simple composition. It has some pretty gem quality to it. This is more like this is about the size of a walnut from Australia, and we have some of this material we use in our research here. But anyway, it's a simple composition. It does take a few other elements into its structure in the periodic table, some of them in small amounts. Hafnium is one of them. Hafnium follows zirconium. This is the geochemistry lesson here today. Hafnium is very much like zirconium in its crystal size and charge, and so if there's a space for a zircon, there's a space for hafnium, and so hafnium follows zirconium around like a little puppy dog. 40 to 1, all right? So for every 40 zircons, there'll be a little hafnium following along. The most important thing about zircons, for our purposes, is that they take a little bit of uranium into their structure when they crystallize from a magma. So it's a trace amount of uranium. Uranium, as you know, decays 2 isotopes here to lead isotopes at a known rate. And the most wonderful thing about zircons, almost all of them, is that while they'll take in some uranium, they just sort of refuse to take in any lead. And so you start off with a system that has no lead, it has some uranium in it, and it works like a what do you call these things? Yeah, hourglass, where you start at the beginning of the Earth, say a zircon forms here, it has all this uranium. Today, a significant amount is decayed into lead, and the ratios of those two just tell you when that zircon grain was born. It's a fabulous clock, and so it's been extremely useful to answer this question, how old is something? Okay, so I want to show you the oldest material then on Earth that we've been able to find, and I promised old minerals, and it's a zircon. It's found in the Jack Hills of Western Australia. And the work was done on this by John Valley at the University of Wisconsin. Some of us have worked with John and used his laboratory too. This is a zircon here. It's been sliced. It's extremely small. Okay, it's really teeny. So it's like I'll press my fingers together and it's about how big it is, right? And it's been illuminated here with an array of electrons that shows some internal structure. You can sort of see this. This is kind of the core here. You can see this ring here, out here, and more. It's a little bit analogous to tree rings, right, in terms of the growth structure on this zircon. And so the youngest materials that crystallize would be out here on the rim. Well, when John analyzed this one here in the core, it was 4.4 billion years old. Just absolutely astounding. Right back, less than 200 million years after the beginning of the origin of the Earth. Here was this material already that we can still see. It's amazing it's preserved because the Earth's a pretty active place. So this is a remarkable discovery. But there's one other thing that's really cool. This is about what do we know about the conditions of formation. We answered that question about where it was, right? Australia? Okay. Conditions of formation is that we can also look at the oxygen in the zircon, and that's something that John Valley is really good at. And when you do look at the oxygen isotopes, it's a slightly convoluted argument, and I won't take you all the way through it. But the zircons crystallized from a magma that formed from material that must have originally eroded off the land surface. And that means there had to have been water and erosion taking place back at that time 4.4 billion years ago. And so the Hadean Earth looks more like this, right? Cool waters. And we've already formed some continental crust because the zircons have little crystals of quartz and muscovite in them that are characteristic of granitic rocks. So here we are, 4.4 billion years old, and really the circumstances are ripe for life to appear at any time now. It isn't that searing, hell-like landscape at all. We were ready up and going pretty quick. So that's here. Here's the Jack Hill zircon right there. At the beginning of the Earth. Here we are. Amazing. Just astounding. Okay, that's an old mineral. I want to talk about new minerals. And so there's an organization, it's the International Mineralogical Association, and they have a commission. I have to look at it every time. We always know it's CNM, the Commission of New Minerals Nomenclature and Classification. They act as a sort of a jury to review proposals for new minerals, and you submit these very complicated sorts of proposals with the crystal structure and the chemistry and all of the other information you would like to have, and then they can approve them. I want to give you an example of just looking for minerals that that have carbon in them, that are carbon-bearing minerals. This is one from Chile. It's really gorgeous. Not one that I had anything to do with. I just was looking for a really pretty picture, and this is pretty good. So, a decade ago, scientists got together and formed the Deep Carbon Observatory, which now has thousands of earth science participants from around the globe looking at what carbon is doing in the Earth. From the deep interior, it's there as diamonds, it's hydrocarbons in the surface, it's in the atmosphere as CO2, it's in the oceans dissolved there, and it moves around in these various and different reservoirs. So this is a really a great initiative. One of the things they decided to do was say, how many carbon-bearing minerals are there in the inventory? I mean, just how many do we have? And most of you know at least one carbon mineral, and that's calcite. That makes up limestone. Very, very, very abundant. There's a lot of it all over the globe. Well, you can do the inventory. You just go to the list of the 5,000. At that time, it was about 4,800 minerals. And sort it for carbon-bearing minerals, and you get 403. So out of all of there are 403 minerals that we know of on the surface of the Earth. Now, the way that minerals behave follows a kind of mathematical relationship, which I'm not going to go into here, although at the end, if somebody wants to know, I can give you an explanation for it. But it allows you to predict what the ultimate number is of set of minerals, or of all the minerals on Earth. And the prediction is that there ought to be about at least 548 carbon-bearing minerals on Earth, say 550, which means, of course, we're missing 145. So so we set out to have the carbon mineral challenge, and this started in 2015, and it said, how many new carbon-bearing minerals can we find by September 2019? That was last month, right? So the door closed last month. Time's up. What have you got? And the answer is 31. So over this period of time, 31 new minerals were found that have carbon in them, and this is one of them here from Chile, another group. Our group here, Utah was involved with the description of five of these out of the 31, and I'm going to just show you a little bit about these. Here's one. This is from the website of the Carbon Mineral Challenge. This mineral is called foxite. Doesn't have anything to do with the foxy color. It has to do with, it has phosphate and oxalate. So this is the first mineral. This is for the chemists in the audience here. This is the first mineral, has phosphate and oxalate groups. Oxalate is a C2O4. So it's an organic compound, which is interesting. Oh yeah, and what else do we have here? Here's the discovery team, and I want to mention Tony Camp, and I'll come back to him, but here's the people, and Joe Marty down here. Tony's a crystallographer, and Joe is what I call a mineral whisperer. He finds minerals, and he understands minerals. He looks, if he sees a mineral that he doesn't recognize, I think it's almost for sure a new mineral. I mean, just no question about it. It's encyclopedic. So anyway, the other interesting thing about this has nitrogen in it. Not a lot of minerals have nitrogen in them, but this one does, and it's in the form of ammonium, which is NH4. And so we might be wondering, where is this nitrogen coming from? Well, I'm going to give you a clue here we could think about. This is coming from the Rowley mine in Arizona, where there are a lot of bats in the mine. They're like caves, right? They're great places for bats. So this was a foxite, first phosphate oxalate. And then another mineral here. Guess who this is named after? David Brown, yes. There was already a brownite, right? So David Brownite. This is a second mineral with phosphate and oxalate groups, so that's interesting. It also has nitrogen in it. Very interesting. And one of the reasons that I've been working with these minerals is, and working with these other collaborators, is that we're pretty good at analyzing nitrogen on the electron microprobe. That's not normally done. And so we've established this ability to do this. And, well, it's, So, but the question, it's not, we haven't solved this answer yet. So here we are, right? Animal, vegetable, or dynamite. Because in this mine, up above the mine, this is in Arizona, our saguaro cactus, right? Is this a saguaro cactus? Saguaro cactus. Whose roots extend down into the roof areas of the mine, and so we could be getting the nitrogen from the plant material there. There's also decaying dynamite in this mine, and dynamite is loaded with nitrogen and as an explosive, so that's a possibility. And then the other, well, it could be bats, right? What do we mean by bats? I'm sorry. Bat excrement, right? For kids here who may not know what excrement is, I'll save you the embarrassment of asking your parents. It's poop, right? Just a fancy word for poop. Bat poop. Okay, so it could be bat poop. So fortunately, there are some people here at the university, Turi Suring is one of them, and we could run the carbon isotopes on these associated minerals and decide whether or not, because these are distinct in their carbon isotopic ratios. And the answer is bats. Indeed, these are bat poop minerals. Bat guano would be perhaps more formal. Anyway, so we know this about these. Okay, so that's two. Back to the mineral challenge. Uroxite, which we discovered, is the first organic uranium mineral. Very interesting. But again, intimately tied then to organic evolution and biological processes, which is really quite important. Found in 2 mines down in Utah down there. And I think, oh, this is in press, hasn't yet come out. And I think one more. Marowitsite is a uranium carbonate. And a lot of carbon-bearing minerals are carbonates. And I'll just leave this one here. There's not too much more to be said about it. Interesting minerals. And then finally, I want to turn to really modern day, although some of those minerals obviously were crystallizing just yesterday, here at this end of this, where we are today, and thinking about living in the Anthropocene. So, welcome to the fabulous Anthropocene. And the Anthropocene hasn't quite been formally approved yet. Margie, is that right? Not yet, but I think it will be. I think it's almost inevitable. But it's in common use now, referring to really the time starting not very long ago where where humans as geologic agents have been prevalent and have been driving the geological evolution of the planet. So, and I want to convince you then maybe that humans are playing a role in the evolution of minerals on Earth as we do this. Well, that's true. We were looking at that just thinking about a mine. We'll come back to this in a minute. So this sentence just says it hasn't been approved yet. When we decide that there's going to be some time interval, you have to decide when it starts. And you could start this modern era with agriculture, or the development of agriculture, or with the Industrial Revolution and putting CO2 into the atmosphere. Others have suggested a time marker would be the time of open-air testing of atomic and nuclear weapons, starting in 1945 and running through the 50s. Because that puts a marker globally in sediment and ice and too. So we can... it will be debated what it will be. I'm using this as a segue into talking about uranium mining in southeastern Utah, which was supplying some of the material, of course, that was used for weaponry and also for nuclear power plants. So we're looking at this area here. Here's a mine that's been gated up here, but allowing for bats to get in and out, right? We want that. So here, oops. Bob Hazen again wrote a paper 3 years ago, or 2 years ago, 2017, on mineralogy of the Anthropocene epoch. And at that time, in 2017, when it was published, they had a list of 208 minerals that had been formed in the Anthropocene. They had basically they were younger than me, all right, younger than me. And 17 of those, that 208, we'd already described. Since then, we've actually described another 29 more to add to these minerals of the Anthropocene. Many of them are forming in the uranium mining districts in southeastern Utah. So here's Utah in green. This white area is this block of this down here. So the Colorado border is here. Arizona border is about here. And in this area, there are, according to the Department of Energy, over 1,150 mines that were drilled here, mining running dominantly from about 1945 to 1970, when most of it came to an end. So all of these black and red dots in here are mines. The colors are just mining districts. And extracted from this, something on the order of 11 million tons of uranium ore was pulled out of the ground here. But you can see most of it in the Morrison Formation is honeycombed through with these tunnels that are all drilled through here. And in these tunnels, then, is where we find these minerals. And here, just to mention on the mineral team, discovery team, here's my mineral whisperer, here, Joe Marty and Tony Camp, looking at some of these incrustations on a mine wall. John Hughes at the University of Vermont is a crystal chemist and crystallographer. So John and Tony are the crystallographers. I do the work to determine the chemical composition of the material using the electron microprobe here. And we work often with other people from around the world on various aspects of this mineralogy. Okay, so just to give credit to these guys. And this is what Tony Camp and John Hughes do. This is a mineral called vanarsite. It's a vanadium mineral. And this is the crystal structure. It's much more complex than the zircon. I'm not don't worry, I'm not going to take you through this crystal structure. I'm just putting it up here to show you. It's complicated. But we're locating every element in the structure, from the vanadium to the arsenic, and then down to the calciums and the oxygens, and even these tiny little circles are all the hydrogens in there too. So locating every one of these, it's really a tour de force to be able to figure out these structures. They're complex. And these minerals, they're not, this one's not very pretty. It's a dark sort of vanadium thing. Are called it's a mouthful. Polyoxometallites in the solid state literature. It's a cluster of metal atoms bound by oxygen. These often are forming in liquids as self-organizing anions. But thousands upon thousands upon thousands of these have been synthesized for industrial purposes. All kinds of these things. Catalysts, coatings, sorbents, sensors, nerve gas degradation. Sarin nerve gas can be broken down by using those things. Polyoxymetallites. Dyes, anti-tumor agencies, antivirals, cancer antagonists, quantum computing. Any number of different things. So it's a huge industry. But there are only about 24 or 24 or so of these that are known, structures that are known in nature, and we've described a number of them. And so they're useful, and some of the ones that we've found haven't been synthesized yet, and they offer some potential templates for maybe future kinds of design. All right, then I just want to show you some pretty pictures here of some of the minerals that are forming in those mine tunnels. This is caseitis, a vanadium mineral. Leucuride, a uranium sulfate mineral. Ammonium-matthewsite, another mouthful, isn't it? Ammonium, right? And then green lizardite here in ultraviolet light. Absolutely beautiful photograph, I think, from the green lizard mine. So just to make sure we sort of understand what the process is here that's forming these things, because these are forming since the mines closed in about 1970 and since. But if you imagine like you're in a mine, I'm not going to turn the lights out, but you know, we're in a mine surface here. We've hollowed out this area, but groundwaters are percolating down through from above, and they are becoming slightly acidic, mostly from interacting with pyrite as it oxidizes. So they're mildly acidic, and they encounter some of the original ore material that was there. Uraninite, vanadinite, some of the ore minerals, dissolve that uranium into solution, and then it comes down and it seeps out on the walls of the tunnel here, and maybe puddles down on some bat poop, you don't know. but at any rate, and then dries up. And as it dries up, these things come out as salts or crusts and solidify. And so that's the process that's going on to produce these beautiful things. All right, we're almost done. Just one other one that I wanted to just mention. Minerite, it's another ammonium uranium sulfate mineral. One of the nice things about finding and describing a new mineral is you get to name it. And I don't know if many of you are familiar with Lisa Meitner, but it's a remarkable story. And so I want to just spend a minute to tell you her story, and then we can move on. She was born in Austria in about 1878, moved to Germany, had studied physics, and she became the first female physics professor in Germany. That was her first accomplishment. And then in 1922, she described a particular interaction of electrons with solids. In 22. A year later, a person in France, Pierre Auger, described this process as well, independently, and it's been known ever since as the Auger effect. Of course, it should be the Meitner effect, because she had described this first. Then in 1938, so this was just before the Second World War, but the Nazis were coming in, were asserting their influence in Germany. She was Jewish, but she teamed up with Otto Hahn, and they performed an experiment of blasting uranium with neutrons, and they split the uranium atom. So this was the first production of fission, nuclear fission, atomic fission. At that same time, she fled to Sweden to escape the Nazis, and led an incredibly rich and fulfilling, successful career as a physicist in Sweden. In 1944, sort of a repeat of the 22 travesty, the Nobel Prize was awarded to Otto Hahn for the discovery of fission of uranium, ignoring the equal contribution of Lisa Meitner to that effort. And the Nobel Committee finally in the 90s opened up the sort of the portfolio and looked at this and conceded that this was really a travesty of justice, scientific justice. The irony, I suppose, is that then the Germans created in 1955 the Otto Hahn Award for the grand prize in physics, and she was, of course, the first recipient of that award. Absolutely amazing. She lived to be 89 years old, dying in 1968. So we thought it was one of the few, least we could do to recognize her contributions. And this is what the structure of minerite looks like. Okay, so where does this get us just in thinking about these minerals that were growing in the Anthropocene in southern Utah? First of all, I think we can see that human activity, mining in this case, has increased the rate of formation of new minerals. So we're making minerals at a newer rate now because of the effects of humans disrupting the landscape or the geoscape. These new minerals, with very complex atomic arrangements, as I've shown you sometimes, are telling us a little bit more about the conditions under which uranium sulfate carbonate minerals form and the solutions that lead to them. And that provides information then on what I think is important about uranium mobility in post-mining areas. This is actually, we know it's mobile because it's obviously moving around and then reprecipitating in these minerals. And so that's important, I think, in understanding here if we want to be thinking about remediation for mine tailings or thinking about storage of radioactive materials in geologic repositories. This will have some bearing on that. Okay, last piece. I don't know if anybody recognizes this. It looks like a reservoir in an arid climate, kind of. You can see the embayments here, and here's a tributary coming into the basin. Does anybody? Don't want to take a guess on it? Okay, well, this is on Titan, the moon of Saturn. It's not water, it's methane, liquid methane. So this is a lake made up of methane. It's so cold on Titan, it's about 90 degrees Kelvin, that methane that we know as a gas it rains methane on Titan, and it accumulates in these basins. This is Ligia Mare. The size of this is about the size of Lake Huron and Lake Michigan combined. It's big enough that it's calculated because Saturn's a pretty big moon with big gravity that has tides on it that might be, I don't know, a foot high. But thinking about mineral processes and sedimentation, they're probably tidal flats on Titan, which is interesting. So what I want to leave you with is to think about, imagine what are the minerals that are forming today on the shores of the seas of Titan. Something to really think about. I think it's just wonderfully imaginative. And of course, here's the artist's conception of that. The seas, methane, some ethane maybe, and whatever these materials might be. And there's a lot of speculation about that. The wonderful thing is, we're going to find out. Titan is the next target for NASA. It's called Dragonfly. It's going to send sort of drone-type things there. They're going to fly around. 2034, we're going to arrive at Titan, and we'll be able to find out what the minerals are on the shores of the seas of Titan. And with that, I think I'll leave you. Thanks.